Good afternoon, and it's a nice coffee. It's 20 to 30 minutes approximately that we will have here. As I know, most of you, or all of you, know already Jiachong.
Yes.
As you know. So I am very happy to say that it's a pleasure that he's at the end of his work in his PhD. And of course, it's a good opportunity to have a speech from him about his work.
Yeah, like defense.
Not yet, not yet.
Yeah, I hope. My only chance.
The floor is yours, Jiachong. Explain what you is interesting for us.
Okay, good afternoon, guys. Thank you for coming. And also thank for my professors, one here physically and one online. I don't know if he can still speak or not. And thank you for your inviting and for your participating. So today I'm going to present to you my last chapter of my thesis, which is a numerical application in the segmental tunnel leakage problems, which is more related to CIMNE, but I have to be more about numerical part. So, I think I put the wrong button. Okay, so my presentation is gonna be divided into 4 parts: research backgrounds, and then I will going to introduce a special case, a deep tunnel project in Shanghai, and then I will propose a numerical-based computational framework, which allows us to assess the long-term leakage impacts. And finally, I'm going to share with you my interesting results in discussion. So at the beginning, I want to introduce this special tunnel type to you because you are not working with tunneling except for my professors. And this type of tunnel, which called segmental tunnel or shear tunnel, is a discontinuous underground structure, which is composed of different rings and different segments, so that we have different joints, including longitudinal joints, circumferential joints, and T-joints. And since the stiffness and the water tightness of these joints are much lower than the concrete, reasonable, right? So we have to pay more attention to these joints in the structural behavior and hydraulic behavior. So the in-situ investigations also indicates that we have to pay more attention to the joints. So now I'm showing you the leakage defects in hydrometric line 1. And the results indicates that the leakage at joints, well, typically accounts for over 90% of the leakage defects. And the results also implies that these leakage effects can be subtle at the beginning, but progressively become more significant in the end and more unfavorable, causing other geotechnical consequences. So these are some extreme geotechnical consequences. So first, it can cause ground movement and landslide or sinkhole, which is here is super extreme scenarios. And furthermore, it can cause structural deterioration and failure on the segmental tunnel itself. So, for example, like lining cracks and failures, and sometimes super large dislocations and joints. And another fact is that the aforementioned leakage scenarios is all infiltration scenarios, which is groundwater inflow to the tunnel inside. But sometimes we have to consider the existence of internal water pressure in some tunnel cases, such as water conveyance, storage, and sewage tunnels. There could be possibility that we have directional leakage condition, which includes infiltration and exfiltration. So the bidirectional leakage induced soil tunnel interaction could be more complicated than single directional leakage scenario. So we have to focus on, in our study, we have to focus on the sealant and leakage behavior affected by joint deformation and internal water pressure. And we also want to explore the mechanical response of the tunnel front system, subjected to infiltration to exfiltration. Okay, now I want to introduce this special case in Shanghai, which is supported by my supervisor in Shanghai, Xin Huang, Professor Xin Huang. And this deep tunnel, which is located in the Suzhou River in the city center of Shanghai. And you can see in the map, it is exactly beneath the river. And it was designed to mitigate the water logging and flooding scenario during the heavy raining system. And in the geological profile, you can see that the buried depth is super deep, about 50 meters, super deep, and it was in the clay strata. So this indicates that any leakage can cause significant structural response and ground response, including groundwater drawdown and ground reaction. And furthermore, this tunnel was designed with a single lining to resist the internal and external loads. So which also indicates that the joint and the gasket are mainly the main waterproof system. And we also consider different scenarios of internal water pressure, including empty tube, full tube, and filling to the ground surface. And in some cases, and there is water logging. So the surface, the water level is above the surface, which can cause infiltration scenario, where the internal water pressure is super high. And we also conduct some experiments, including structural experiments and waterproof experiments, which lays foundation for my calibration work for the numerical model. And now I'm propose my computational framework based on numerical modeling, which allows us to assess the long-term leakage impacts. Oh, much. So here, the most important mechanism I want to capture using the numerical model is the hydromechanical coupling behavior at the joints, not in the strata. So basically, the waterproof capacity of the joint is affected by joint deformation. But at the same time, the joint behavior is also impacted by the soil tunnel interaction induced by the leakage. So it's all coupled. So specifically, in this diagram shows the schematic. So at the beginning, there is leakage behavior. So the leakage behavior changes the seepage field and leakage boundaries. And over time, it has consolidation behavior. Then it changes ground reaction and soil tunnel interaction. And finally, there is tunnel deformation and joint deformation. And because of that, there is possibility that it can cause hydraulic deterioration to the joint, which causes further leakage behavior. So this whole mechanism is coupled, and which dynamically changes over time during 100 years or 200 years. So in my numerical model, how can I capture this coupling behavior? So we proposed a numerical-based computational framework, which enables iterational analysis by developing the user-subroutine based on Abaqus. So this diagram shows how I capture this coupling behavior. So in each step, we have numerical results. Then using the numerical results, we have the joint behavior information, including joint deformation and joint internal force. At the same time, we have the groundwater pool pressure and the time, real time, which is the real time. And using this information, we have the current water flow capacity of each joint. And using this information, we can calculate the leakage rate and put it in the leakage boundaries. Then we can conduct next numerical steps. So this is basically how I achieve this new hydromechanical coupling behavior at the joints. But in the coding, in the programming, how can I determine the real-time sealant and leakage behavior of the joints using the joint deformation and using the joint internal force? So basically, there are 3 steps to go. So the first step is to obtain the compression strain of the gaskets. So using the structural response I obtained from the numerical results, we can determine the bending modes, whether it's positive bending or negative bending. And also we can have the rotation points using the neutral line here. But sometimes the neutral line could be really huge, so which is extreme scenario. The rotation point could be at the edge of the grooves or at the edge of the joint. So step 2 is to calculate the current waterproof capacity of each joint based on the real time, which considers the aging behavior and the compression strain of the gaskets we just obtained in the last step. And we can determine if the waterproof occurs. So now I'm showing you this 3-dimensional diagram shows the waterproof capacity decrease over time and over openings. So this indicates that the waterproof failure could be triggered by the aging behavior and the joint opening. So the final step to calculate the leakage rate. So first, we can calculate the hydraulic gradient considering the internal water pressure and external water pressure and waterproof capacity we just obtained from the step 2. And then we can calculate the leakage rate based on the cubic law. And finally, we have the no leakage scenario, infiltration scenario, and exfiltration scenario. And we can put it on leakage boundaries. And note that we use the cubic law. We have to be careful about the hydraulic aperture, which should be really realistic to the real scenario. It should be really small, about micrometers. And technically, the framework can be used to any numerical models we have, but here I only propose 2 numerical models. The first numerical model is the one-ring model, which I can focus on the transverse response by the leakage at longitudinal joints. To capture the refined structural response, I use shell spring model. So here, which means here is shell, here is spring. And I also consider different joint stiffness, which is obtained from the test data. So the next model, the second model, is a large-scale 3-dimensional model, which allows me to focus on the longitudinal direction, the response, where the leakage we have the leakage at central end. But the modeling techniques is exactly the same as the previous model, but here I have to have an extra consideration of the circumferential joint, which allows the ring-to-ring connection. Okay, finally, I can have some interesting results to share with you based on the numerical modelings. So the first, which is most important, the results indicates the hydromechanical behavior of the joints. So now I'm showing you the relative rotation of J7 and eccentricity of J7. And here we can observe that after 40 years, it changes because the waterproof failures. So after that, the rotation increases, the eccentricity increases. And we also compare these results with non-couple case, which is dashed lines. So in non-couple case, the waterproof stage increases to 50 years with smaller structural response. This is a good result, indicates we have to consider the hydromechanical behavior at the joints because further rotation will cause further deterioration hydraulically. And here is the structural response induced by single joint leakage. So the results indicates that any single joint leakage can cause structural deterioration for the whole ring, and the joint opening has significant impact. So for example, when the opening is 1 millimeters, there's no leakage at all because it indicates good construction quality. There's no leakage at all. And in some unfavorable openings, the leakage can cause overall settlement up to 10 millimeters and slight ovalization trend when opening is 11 millimeters. And this is all because of the consolidation of the strata. And here I'm also consider different impacts of single pair of gaskets and double pair of gaskets. So here the solid lines indicates single pair, the dashed line indicates double pair. We have double pair waterproof system. So from the left figures, we can indicate that the double pair of gaskets can mitigate the structural response with longer waterproof period. So it increases the waterproof period by using double pair of gaskets. And this is actually can be explained by the right figure, which is the waterproof capacity of each joint. Let's look at the dashed line. It increases the waterproof capacity compared with single pair of gaskets, mainly at the waist, because here the tunnel is at negative bending moments at the waist. So where the double pair of gaskets can have a good enhancement on the waterproof capacity. And we also analyze the impact of internal water pressure. So here I'm showing you the eccentricity of the joint and waterproof capacity of the joints. Since it's really easy to understand when there is internal water pressure, the axial force of the lining decreases, so which enlarges the eccentricity. And so in some extreme scenarios of internal water pressure, the eccentricity could surpass the joint height, which is really unfavorable, but eventually, well, the rotation point will be at the edge. And because of that, because of the rotation point changes, it enlarges the water, it decreases the water capacity, which is super significant. Okay, here I'm showing you the seepage field of the strata impacted by the internal water pressure. So it's a seepage field over time and over internal water pressure. So there are some conclusions. So the infiltration can transform into exfiltration as internal water pressure increases. And in some special scenario, only small leakage occurs when internal water pressure is 500 𝗥𝗣𝗥𝗧, because there is a balance between internal water pressure and external water pressure. And furthermore, the leakage process is progressively increasing over time. This is mainly because of gasket agent, but also can be attributed to the hydrochemical coupling behavior. Okay, so here for a 2D scenario, I'm using one figure to conclude all the mechanism we mentioned, including the infiltration, including the internal water pressure and long-term leakage. So in the white quadrant, there's no leakage, but it has an ovalization because unfortunately there is tunnel effect. So we have certain rotation at the joints, and over long term after infiltration, the ovalization increases because of the consolidation and so many mechanisms in the strata. And we can observe the increasing in the joint. And now let's look at the blue quadrants. There's no leakage, but we have the internal water pressure. This induces the rotation point could switch to the edge of the joint, which is really not good results. And finally, we have the purple quadrants, which represents the exfiltration scenario. The rotation point could be really large still because we have the internal water pressure, but the structural response is totally opposite from the infiltration. So it's not become ovalization, it's more become a circle. And so here, in addition to the two-dimensional scenario, we also consider the three-dimensional scenario. So in these scenarios, it's more complicated because we have to consider the longitudinal sediments, which can induce further leakage because of ring-to-ring connection. And furthermore, the consolidation is localizedly distributed in the longitudinal direction. So this is a more realistic case, but the two-dimensional scenario is more unfavorable because it imagines there's no difference in the longitudinal direction. So I'm only briefly showing some results of the three-dimensional model. So here is the settlement increments and longitudinal force. There are some conclusions. The first is the settlement trough can turn into a heave when infiltration transforms into exfiltration. And this is because the consolidation behavior transforms into unloading behavior at the strata. And second, the settlement trough has an approximate width of 300 meters. This is crazy because there's only one ring has leakage, but the impact is super widely distributed. And finally, the infiltration and exfiltration induces opposite longitudinal force, which indicates downward bending or upward bending. Okay, based on the numerical model I proposed, I think I can have more future work, or you can have more future work. First, I think I can implement more sophisticated theories to the framework to capture more realistic situations, such as nonlinear rotation behavior of the joints and enhancement of double pair gaskets, how it enhances the water capacity more sophisticatedly. And the second, I think the framework can be extended to more extreme scenarios, such as like excavation or uploading, surface loading, these scenarios. And finally, I think it has potential to assess the leakage state using the in-situ monitoring data. And thank you, that's all my presentation. Please share your comments with me or other ideas. Thank you. your comments with me. But you are a geotechnical engineer.
Yeah, but the tunneling, I don't have any idea.
Oh, imagine it as a pipeline.
I have a question, but it's not numerical. It's not a numerical question. It's more regarding as from the practice point of view. When you have a lot of problems inside a tunnel, when you have after 100 years, you said in a tunnel that you have a significant water table. If you have a significant problem regarding leakage, what can you do?
I think the real situation could be like when there is leakage, we fix it. When there is leakage, we fix it. Not
How do you fix it?
some grouting, cement, or just replace the segment by steel plate segment.
So very localized intervention, do you think?
Yeah.
Because if you are grouting, introducing some grout in the part in the joints that are leaking, or outside also sometimes they introduce grouting outside to make a larger barrier for the leakage. This is a question that somebody can ask.
Yeah, the engineers they said the grouting is more important than the gaskets. They said that.
This is a traditional way to proceed, but when you have a tunnel like this one, that you can after 100 years you can have leakage in many places. It can be crazy.
Yeah, but it starts from the joints. Finally, it turns into everywhere.
No, but if you have leakage in all the joints, it's a hard work.
Yeah.
Look, in Switzerland, normally all mechanized tunneling, all segmental tunnel linings, before placing them in service, they do an inner lining of plain concrete. Do you think this can help?
Yeah, definitely, especially for the sewage tunnel or stop water conveyance tunnel. It's common, but in this case, it's special because it only has one segment. There's no segment lining, which the waterproof capacity is a huge task for this case.
So they will not place an additional plain concrete lining. No.
Yes, I think so. There's no second line.
Oh, it's a bit to say this. So all the water tightness is relying in the gaskets.
Or the floating. if there's any.
Okay. Good.
Thank you, Professor. I don't think I can allow them to talk. Okay, you comment if you have any. You work with pipeline flow.
I may have a question.
Yes, please.
Not the question, just a little bit curious. What material you define the soil layers?
Oh,
Elastic or plastic material?
only more clone.
No clue.
Yeah, there is some problem because clay strata.
Yeah.
The question is really critical.
Because I also have some experience in Abaqus, and to my knowledge, it's very hard to convert when you use plastic materials, especially for the multi-soil layers.
Yeah, and it's clay strata and soft soil. Using simple constitutive model could have some problems in here. Thank you.
Yeah, I will.
Please.
Very nice presentation, firstly. I learned a lot about tunnels. So, so you mentioned you were working on the case study, right, in Shanghai, the tunnel.
Yeah.
So I just wanted to know a bit like how do you collect those leakage data, or because you use it to validate your model as well, right?
For this case,
That's a pretty long tunnel. So how
for
do
this
you?
case, it's still under construction. There's no data.
Okay.
And For the leakage information I have, it's from other tunnels, like metro tunnels, where people can access,
Okay.
and not by me, of course, by the metro engineers or some people. But for this case, no, it's still under construction. Not complete yet.
Yeah, so that's gonna be a case study for the future, I guess.
Yeah.
So how you gonna implement it over there?
I don't know, and there's some problem. There is internal water sometimes, and people cannot access into this tunnel. You have no idea if there is leakage or not.
Okay, so I saw in the future work there's gonna be some kind of in situ monitoring as well, right? So
Yeah, the robot can come in.
so you have some kind of sensors so that you can use it as kind of leakages.
Yeah. Thank you. That's new topic.
Yes.
Really coming in our scope. Really. I think. Any problems? Oh, I mean,
Question, bro. If I remember, you did the modeling in the city clay. Yes, this was in city clay.
yes.
Then with the metro line, it's not always in the same line. Maybe, for example, clay, city clay, or silt. So the rate of the water leakage is different in each layer. So if you consider it or not.
No. And in Shanghai, the subsoil and clay is super thick. I can promise there's always clay, but it could be different clay. Not like in Barcelona, it could be different, like rock and clay. But in Shanghai, it's a consistent clay, like 50 meters, I think, to 6 meters deep per layer. Okay, thank you for.
No, because in the metro line, because the layers of the ground is different, they are changing. So if you cannot maintain the line in the same layer, so the water leakage can be different. Sometimes higher, sometimes low. But you're using the same material, so it can be different from place to place.
Sometimes I analyze it when there is rock behind. The seepage field distribution is totally different. But in this case, only clay strip. So there is no really big difference using different clay. Thank you for geotechnical insights. Please.
I know nothing about this subject, so I'm asking. So in this map, you have the tunnel of the subway that touches maybe that is very close to a river.
It's on the river.
It's on the river.
Beneath the river.
So the leakage is caused by heavy rains, right? Does the river has any effect?
The river actually has effects.
Okay.
But in my point of view, I'm only considering the gasket. But technically, from the in-situ investigations, when the tunnel is close to the river or under the river, the leakage effect is more significant, much more significant. But super deep, like 50 meters, I don't know if there's any impacts from the river, under the river. Could be. There is sufficient water supplement from the river.
I can add that if you look at the column of the different clay strata, you can see that the water table is almost at the top.
Yeah,
The
more or
blue
less.
sign, the blue sign. Okay.
More or less.
Quite close to the.
Yes.
The river is maybe 5 meters deep.
Because Shanghai is created by the river. Okay. Any comments from my online professor? Can you hear me? Okay. Wait, there's a group chat. Oh, that's from me. Okay. Thank you. Thank you for participating. And you. What time is it?
Thank you, Jiachong.
Thank you, Professor. Thank you, my friends.